Hey, Dr. Clark coming back at you with another differential equations video. This time we're looking at homogeneous harmonic oscillators. Let's take a look. So earlier we've looked at spring mass models, okay? And we've seen that a mass on a spring can be modeled by this differential equation right here. And this one would be one where you don't have any friction terms. So this is just Newton's second law, ma, right there. If x is position, then x double prime is acceleration. So that's ma. And then kx is your spring force. So you can see here in the diagram we've got a spring force. Now it's possible we could incorporate a friction term as well. It's possible we could incorporate an external forcing term, but this model here is homogeneous, so there's no external forcing and there's no friction term here. It's just the spring, Newton's second law, and the spring force from Hooke's law. Okay, and we're going to use x as our variable with t as our independent variable because we usually think of it sort of sliding, left to right here. That mass on the spring kind of bounces back and forth, and then x is position. And if you had yourself an undamped harmonic oscillator, you would get a solution of C1 sine Wt plus C2 sine Wt, where W is root k over m from solving out that differential equation. We call this simple harmonic motion or free undamped motion. Free because there's no external forcing, and undamped because there's no friction term. And then that solution would have a period, 2 pi over W, and a frequency W over 2 pi cycles per second, right? So this is sort of something we've already seen. What I want to show you, though, is you can take this sine and cosine function here and write them together as a single sine function or a single cosine function. And occasionally that's nice to know. Because when you add a sine and cosine function, actually what happens is they combine together and they will offset from 0 where their sort of home place is. And the amplitudes of the two individual functions will add as well, and they'll add according to Pythagorean theorem. So why don't I just quick show you what we have here in Desmos, and then you'll kind of see what I'm talking about. So the red graph here is C1 cosine plus C2 sine. If I change the frequency, or W here, I can increase the period of the increase or decrease the period, increase or decrease the frequency. So W is controlling the frequency. But look at this, C1 here is 3 and C2 is 4. If you run the Pythagorean theorem on 3 squared plus 4 squared, that's 25. Square root of 25 is 5. And you'll notice the height of this is 5. Okay? And in general, the amplitude of the sum of sine and cosine is always going to come from that. So if I change this, I can figure out exactly what the amplitude of the combined function will be by applying the Pythagorean theorem to the C1 and the C2. So that's kind of interesting. The other thing you'll notice is that a sine function and a cosine function always start at 0 here. Well, cosine starts at 0, 1, and sine starts at 0, 0. But here, the initial point has been shifted back. And you can actually quantify how much shifting is happening as well. So look at this. I've got this a sine wx plus alpha here. This is exactly the same graph, okay? Similar with this cosine, it's exactly the same graph. The frequency remains the same. The amplitude comes from Pythagorean theorem, and the shifting, either the plus alpha or the minus beta, comes from alpha being the arctangent of C1 over C2 and beta being the arctangent of C2 over C1. And you can do a bunch of trigonometry and see why that's the case. You're just going to sort of take my word for it. But if you ever wanted to combine a sine and cosine sum into a single sine or a single cosine, that's the way to do it, using these alpha and beta terms and then those formulas right there. And you'll get exactly the same graph. And so this is in the slides as well, so C1 cosine plus C2 sine equals a sine Wt plus alpha. A comes from the Pythagorean theorem. alpha is solves this equation, tan alpha equals C1 over C2. It's basically the angle on the vector C2 comma C1, and cosine is the angle on the vector C1 comma C2 if you put those constants in there. So I think that's kind of a neat thing, how to combine sines and cosines, and you'll see that in your physics classes every once in a while. For an example, if we take root 3 cosine plus root 1 or plus 1 sine, well, root 3 squared is 3, 1 squared is 1, 3 plus 1 is 4, square root of 4 is 2. So we should get a 2 sine of 1x or a 2 cosine of 1x. And then in terms of what's the alpha and the beta here, you have to look at basically this vector or this vector and take the arctangent. And in the case of alpha, you get pi over 3, and in the case of beta, you get pi over 6. So you can kind of do a problem like that if you're interested. And here's the Desmos graph showing that those three functions are all on the exact same graph, one on top of the next. All right, another kind of interesting thing is we're looking at spring problems in this section, and if you hooked up two springs with two different spring constants in parallel, it would turn out that the effective force of the spring would just be the sum of those spring constants. So any problem that has multiple springs in parallel can be treated as a single spring using this. This may remind you of a circuit that's wired in series and the resistances add. And so basically the effective spring force on a parallel spring is similar to the sum of resistors in a series circuit. If you wire the springs in series, like one on top of each other, they again combine to have a single spring constant, can be treated as a single spring. But the spring constants have to be combined in this way, product over sum formula, and that actually is similar to how resistors would add their resistance when wired in parallel, product over sum. So again, double spring problems can be treated as a single spring, so we don't really need to look at complexity. We can just, consider single springs in all our problems. This is a summary of what you should know coming into this section about how to solve a second order constant coefficient homogeneous differential equation. This is that friction term corresponding to the damper. If B is equal to 0, then there's no friction. We call that an undamped model. If the friction term is small, that is, if b squared minus 4mk is negative here, and this is coming from the Pythagorean theorem. If that b is relatively small, we call it underdamped. There's not very much friction in the system, and so we call that underdamped. In the event that b squared minus 4mk is equal to 0, that's called critically damped. This is when you'd get a double root in your characteristic equation. And overdamped b squared minus 4mk positive, this would correspond to getting two real roots in your characteristic equation. And so the solutions that correspond, well, if there's no friction, we just get sine and cosine. The undamped motion just goes forever and ever as a sine and cosine function. Underdamped, that's when the under the radical of the quadratic formula is negative, so you're going to get imaginary numbers. You get a complex solution, and we saw that you can write this as e to the st sine of wt, e to the st cosine of wt, where s and w come out of the quadratic formula. Critically damped, you get the double root, and so you get e to the st and t e to the st, where s is that double root. And then overdamped, you're going to get two real roots, s1 and s2, so you get e to the s1t and e to the s2t. In all these cases, if these values m, b, and k are all positive, then the values of s will always be negative here. You'll always have some friction, and so you'll have a decaying exponential, decaying exponential, decaying exponential. Energy will always decay out of the system. So that's sort of a review of what we've seen. We're going to be using this sort of as known for the rest of the video. And in this example here, they want us to classify the type of harmonic oscillator being modeled and then give the general solution. And they've given us 4 different problems, and they're wondering if we can classify them correctly. So let's take them one at a time. The first one, x double prime plus 2x prime plus 2x equals 0. We write down the characteristic equation. We find the roots. It turns out we have complex roots, -1 plus I. And so the solution is going to be c1 e to the -1t cosine of 1t plus c2 e to the -1t sine of t. That's the general solution that comes from when you get complex roots that we just saw the slide before. And we're going to classify that as underdamped because that b squared minus 4ac term, or b squared minus 4mk, is negative, so that's called underdamped. I drew a graph here. You can see that the oscillation persists and then decays down. So instead of, asymptotically going to 0, we actually do get a bounce in the spring coming from the fact that we have sine and cosine here. The second example, there's no friction term, so this is going to end up being called undamped. The b term is 0. If you write the characteristic equation and find the roots, you get pure imaginary here. So when you write e to the 0t cosine of 2t, you just get cosine of 2t and sine of 2t. Here's a graph. You just get persistent harmonic motion or simple harmonic motion because it's an undamped problem. Our third example, we've got, looks like a little bit more friction this time. We write down the characteristic equation. We can factor it to find the roots are a double root of -3 and -3. If it's double rooted, that's that critically damped case where that discriminant is equal to 0. So your solution is c1 e to the -3t, c2 t e to the -3t, critically damped. And you'll notice in the critically damped case, we don't bounce past 0 and come back. We asymptotically come in towards 0. The final case, which is what we call overdamped, that graph is going to look almost identical. It's just going to asymptotically come in towards 0. The way you solve it again is you take your homogeneous differential equation, you write the characteristic equation. In this case, we can factor it into two roots, two real roots, -3 and -2. And so our general solution is c1 e to the -3t plus c2 e to the -2t. And that b squared minus 4ac term is positive in this case, so that's overdamped. We got lots of friction, and so that spring only just drags itself back to 0. It doesn't have any bounce to it at all. All right, so hopefully that gave you a sense of the kind of homogeneous problems that you get when you model simple harmonic motion or spring mass damper problems. In the next video, we're going to look at non-homogeneous problems where we add in that forcing term. We'll see you next time.